The brain is a super fascinating organ, and we have about 85 billion neurons, and every neuron is 1,000,000 times slower than a computer chip. And yet, the brain does incredible things. But what that means is that if you want to get data in and out of the brain, you have to be able to talk to a ton of different neurons simultaneously. And that's where the emphasis on building these high-speed, high data rate devices came from. My name is Matt Engel. I'm the CEO and founder of Paradromics. Paradromics' mission is to transform otherwise untreatable health conditions in brain health into solvable technology problems. We're fundamentally building a medical device to serve unmet needs. And what that does is it allows us to connect to the brain and receive data from the brain. Those medical devices are prescribed by physicians, they're implanted in patients, and they're paid for by private insurance companies. I think a reasonable expectation for these kinds of devices would be around $100,000 per device. The first patients to benefit from Paradromics technology will be patients who have lost the ability to communicate due to paralysis. People with ALS, spinal cord injury, who are trying to get back to normal communication with their families. But the same kind of device can also read out things like whether someone is depressed or whether someone's experiencing chronic pain. And so where we see the real clinical impact of BCI is that it's going to become a first line for many people with neurological health conditions.
My name is Vikash Gilja. I'm the Chief Scientific Officer at Paradromics. The reason we've chosen to focus on motor and speech is because these are well trodden in our research community and the science exists. And so Paradromics can take this science and apply the right engineering to get us from research to medical device. The Paradromics system involves implanting an electrode array on the brain. This implanted device generates data and requires power. And so that data is sent through this cable. Power is received by the cortical module through this cable. This cable then connects up to a chest-based internal transceiver. Now, this internal transceiver is designed to be fully implanted so that there's no wires or ports from in the body to out of the body. And the way this is achieved is that power is wirelessly transmitted to this device, and high-throughput data is transmitted from this device to outside of the body. The device does not require any charging. The one thing you would have to do as a user is go through a brief calibration routine to learn that mapping from electrical signals to intention. But once that mapping is learned, the system can be used. And what we know from existing research in this area is that we can sustain that use over days and weeks.
My name is Kimiko Nakajima. I work on developing processes or selecting the materials that we would like to use to build our cortical module, which is the brain implant portion of our system. This is the feed-through, so the component that's going to go into a package of our neural implant that's going to be protecting the computer chip inside of our implant. And I am looking for any foreign material that might be on the surface of the part. This is our neural implant, and what we are looking at is the package that has a computer chip inside, and on this side of the package we have hundreds of electrodes that detect neural signal from a brain. Every single dot that you can see on this screen is an electrode that's attached to the package. And one of the things that we do in this inspection lab is to make sure that these electrodes are very well attached to the package.
Our first human trial will be in 2025. I would expect that we would have commercial approval to sell the product no earlier than 2029. We see that the first 1 million people to get brain-computer interfaces are going to be getting them to treat severe medical conditions. I think there could be a different conversation 20 years from now, and some of those devices could also have consumer applications. But in the meantime, we're really focused in building safe, reliable, robust devices for people with physical and mental conditions.